So today we are going to go over some of the general properties and introductions of acids and bases, things that were basically covered in the POGL yesterday. And then what we're going to do is we're going to learn a little bit of new things like acidic nomenclature and also more things about conjugates, acids, and bases. So the first thing that we have to kind of refresh your memory about is the definition of an Arrhenius acid versus the definition of a Bronsted-Lowry acid. They are similar, but not exactly the same. So an Arrhenius acid is an acid or a substance that when added to water increases the hydronium ion concentration of that particular new solution. Hydronium ions are the H3O plus, but sometimes they're referred to as just H plus, or sometimes they're referred to as just protons. Now, to sort of refresh your memory on that, a neutral hydrogen atom, protons, neutrons, and electrons, has 1 proton, 0 neutrons, and 1 electron. But a hydrogen ion loses an electron, so it has 1 proton, 0 neutrons, 0 electrons. So oftentimes the hydrogen ion is referred to as a proton. So anytime that I'm talking about protons being donated or accepted or whatever, I'm usually just talking about a hydrogen ion being transferred. So down below I have a picture of water and a proton, which could be H plus, and the water has accepted this proton to become the hydronium ion. So in this case, we're showing what the hydronium ion actually is. It's a hydrogen with 3 protons or 3 hydrogens on it. Sorry, it's an oxygen with 3 hydrogens on it, and it has a +1 charge. Now, general properties of acids is that they tend to react to neutralize bases. They tend to change the color of acid-base indicators, as shown in that diagram on page 1 of the POGL. They all have a sour taste. They have the common property of producing hydrogen gas in single replacement reactions with metals. So for example, magnesium plus HCl makes magnesium chloride, which is aqueous, and then hydrogen gas, which is given off, and they all have a pH value less than 7. Okay? How do we know that all acids taste sour? Somebody had to be the guinea pig.
Who would be the guinea pig for this class?
In this class, most likely I would have 2 guinea pigs.
Nate and Chase.
Oh yeah, Nate and Chase are definitely the first 2 that come to mind. So here are some examples of acids. You don't have to memorize anything about this particular slide. I'm just giving you an idea as to where you might find some of these acids that you may or may not have heard of. Sulfuric acid is the acid found in car batteries. Nitric acid is used in the production of fertilizer oftentimes. Hydrochloric acid is your stomach acid. If you've ever had the sickness and the next day you woke up and your stomach and your esophagus was burning, it's because you threw up stomach acid and it ate a layer of your esophageal cells off of your esophagus, and that's what you're feeling. Citric acid is found in lemons, limes, and other citrus fruits. Phosphoric acid is the tangy or sour taste in most sodas. Acetic acid is dissolved in water to make common vinegar, and carbonic acid is usually what we use to carbonate sodas, but it's also found in sodas as well. So those are some examples. What now?
It's in the ocean.
Oh, okay, also in the ocean. Now, definitions of bases, there are 2 that you have to be responsible for understanding. There is the Arrhenius base, and there is the Bronsted-Lowry base. The Arrhenius base is any base that increases the concentration of the hydroxide ion when dissolved in water. Most Arrhenius bases are soluble ionic hydroxides. That is a metal and the polyatomic ion hydroxide dissolved in water. Now, the example that I gave here is potassium hydroxide, solid, dumped in water, makes potassium ion and hydroxide ion. Another one would be something like NaOH and CaOH2. Those are all examples of bases that can be found by dumping them in water, and they produce hydroxide ion and increase the concentration. The Bronsted-Lowry definition of a base is a proton acceptor, and as a result of it, it'll take a proton from an acid. So in the case of the example below, I have NH3, which is known as ammonia, and NH3 will accept a hydrogen or a proton and become the NH4 polyatomic ion, which you are aware of as the ammonium ion. So in this case, we produce the ammonia ion by adding a hydrogen to ammonia itself. Any questions about those two types of definitions, Arrhenius acids and bases and Bronsted-Lowry acids and bases? Common properties to all bases is they react to neutralized acids, they change the color of acid-base indicators, they feel slippery, and they all have pH values greater than 7. So basically, if you get anything on you that feels slippery, it would generally be considered basic. Soap, which is generally slippery by nature, is a base. So when you are washing your hands or your face or your body parts with soap, you are basically putting base on yourself. The cheaper the soap, the more likely it is to dry your skin out. So if you wash your hands and you have dry skin afterwards, it's probably because you washed your hands with a cheap soap, sir.
Water is not a base, though. It's slippery.
Water actually is a base, as you learned about yesterday, in which case you found out that water can be both an acid and a base. Although you probably forgot because you weren't remembering things from day to day. Moving on. Some examples of bases are sodium hydroxide. Sodium hydrogen carbonate is found in baking soda. Sodium carbonate is found in antacids like Tums. And ammonia, NH3, is a general all-purpose cleaner. It used to be the major component of Windex, but they don't use it. It's not the major component of Windex anymore, in large part because people started freaking out because their babies were licking windows after they cleaned them, and they were nervous that the ammonia was going to make their babies sick. I mean, you guys have all seen babies lick a window before, right?
I know.
You've never seen a baby lick a window? No. Like maybe not lick one, but just put its face on a window and like smear its face all over the window. Well, all right. Oh, wait. Yesterday, we briefly discussed the idea of acid and base strengths in our POGL, but we need to make sure that we understand it in greater detail. So the strength of acids and bases depends on how many ions they produce when they are dissolved in water. So here's an example of hydrochloric acid being dissolved in water, and it's producing only ions. The only ions that are producing are the H3O plus and the Cl minus. Another way to write this would be HCl will dissociate into H plus and Cl minus ion. So in this case, we'd have aqueous, and liquid. So when you take HCl and you dump it into water and it completely breaks apart, we refer to that as a strong acid. So any acid or base that when you dump it into water makes only ions, we call that strong. Okay? Whereas weak acids are a little bit different in that weak acids and bases do not ionize completely. And as a result of that, hold on a second. She's at the blood drive. Everybody else is here. Okay. So as a result of that, they don't ionize completely. So what we're getting at here is that the HF dumped into water makes hydronium ion and fluoride ion. But another way to potentially write that would be like this. HF plus water will react to form H3O plus F minus plus HF. Now, this is technically not the correct way to write that, but what I'm getting at here is I'm trying to show you is that the products here include HF. So the acid itself did not completely break apart. So when an acid or a base does not completely break apart when you put it into water, we call that a weak acid or a weak base. Okay? So strong acids and bases completely dissociate. Weak acids and weak bases do not completely dissociate. So if I'm looking at and trying to identify if something is a strong acid, I look at what it does when it's dumped in water, and sometimes it might be written like this, and sometimes it might be written like that. But the big thing is that it doesn't completely dissociate if it's a weak acid. It does completely dissociate if it's a strong acid. Any questions about that? Okay. You also have to learn how to name acids and bases, and there are some rules that you're now going to have to commit to memory. So you learned how to name ionic compounds and covalent compounds last semester. Now you're going to learn how to name acids because it's a little bit different. The first type, there are two different types of acids that you're responsible for understanding. One is called a binary acid, and one is called a polyatomic ion acid. The binary acid has two elements, hydrogen and one other nonmetal. So binary acids always have hydrogen and one other nonmetal, so I'm going to make that X as its general generic format. Okay? We always treat hydrogen as having a +1 charge because it's the proton, and when you write the name for a binary acid, you use the template hydro as a prefix, the root of the nonmetal, and then ic acid. So examples would be hydrofluoric or hydrobromic or hydrosulfuric. Okay? We always write the binary acid name with the prefix hydro, and then we change the ending of the nonmetal ion from "ide" to "ic." So, for example, H2O would technically be hydroxyic acid. So water is actually hydroxic acid. So a human could go to the dinner table and say, "Mom, could you please pass the pitcher of hydroxic acid?" and sound really smart. Okay? Now, the other thing that you have to be able to do is go backwards from it. I'm going to and write the name or write the formula, and I'm going to go through that in a slide in a second. Now, the other thing that you have to be responsible for understanding in terms of acidic nomenclature is that there are acids that are made with polyatomic ions. And most of the polyatomic ions that you memorized earlier this year have alternate forms. Right, so most of you didn't memorize them at all, so good times. However,
Quiz me, Mr. D.
the major difference is in the number of oxygens in the ion itself. The suffix of the polyatomic ion determines how many oxygens are present. So if we say something has a polyatomic ion has a ATE ending, that is the most common form of the ion. The similar ion that has an ITE ending means one less oxygen. So for example, looking at my list of additional polyatomic ions you should be aware of, nitrate, the most common form, it's the one you had to memorize, is NO3 minus 1. Nitrite, didn't have to memorize it, is NO2 minus 1. Okay? Chlorate, something you had to memorize, is ClO3 minus 1. Chlorite is ClO2 minus 1. The only difference is one less oxygen. Sulfate, something you had to memorize, SO4 minus 2. Sulfite is one oxygen less, so it's SO3 minus 2. Phosphate is PO4 minus 3, something you had to memorize. Phosphite is PO3 minus 3, something you did not have to memorize. But now that you see ite versus ate, you should be able to correctly come up with the appropriate polyatomic ion. Now, how polyatomic acids work is, first of all, they never use the prefix hydro. This is how we keep polyatomic ion acids separate from binary acids. And all we do is we identify what the polyatomic ion is and change the ate suffix to ic and then add acid, or the ite suffix to ous and add acid. So for example, HNO3 becomes hydrogen and is hydrogen and nitrate, and they make nitric acid. H2SO4 becomes sulfuric acid. H3PO4 becomes phosphoric acid. HNO2 is hydrogen and the nitrite ion makes nitrous acid. H2SO3 is the sulfurous acid, and H3PO4 is the phosphorus, or PO3 is the phosphorus acid. Now, you don't have this slide, but you should have some room to be able to write these examples down with me, okay? So the first thing that I'm going to notice here is that this is hydrogen and a polyatomic ion acid. It's hydrogen and a polyatomic, which means that I don't use the prefix hydro. I have to go ahead and locate which polyatomic ion it is. So PO4 is the phosphate ion, so it becomes phosphoric acid, which I have to, this one is weird, O-R-I-S. Phosphoric acid, okay? So that's a polyatomic ion. Here I have hydrogen and a nonmetal, so this is binary, and so that means I'm going to use the template hydroic acid. So Se is the nonmetal selenium, so it's the selenide ion, so it becomes hydroselenic acid. Okay? Now, in the next set, I see the prefix hydro and the IC, so that tells me that it has to be a binary acid, which means that it's hydrogen and a nonmetal. So I'm going to start with hydrogen, which I know is a +1. I'm going to see that the iode is the root of the iodide ion, which is -1. I crisscross the charges down, and I get HI. Chlorous acid, I see does not have hydro, so that tells me that it is hydrogen and a polyatomic. Okay. The suffix OUS tells me that it's one less oxygen than the chlorate, so it tells me that it's the ite form of the ion. So chlorous is ClO2 -1, and because it's an acid, I have to put a hydrogen in front of it. I crisscross my charges, and I get HClO2. Questions about that? Because you are absolutely going to have to do that for homework tonight. All right. Any questions? We got it?
How do you do it?
Huh?
How do you do it?
How do I do what?
That.
I literally just did it.
Yeah, I know. You said, is there any
I
questions?
even know how to do it.
Like, I'm so confused. I was
Okay.
trying to write the whole time.
Well, good thing there's going to be homework time. There are hundreds of acids that exist on the face of the planet, okay? There are only 7 that are strong acids. So I tell my AP kids that they should memorize the 7 strong acids, and after they've memorized the 7 strong acids, they should just assume that everything else is a weak acid. So, with that in mind, in this particular scenario, there are 7 strong acids that you technically don't have to memorize, but you do have to be responsible for understanding what they are. If you're planning on taking AP Chemistry anytime in the future, you definitely should memorize them, and they are hydrochloric, hydrobromic, hydroiodic, sulfuric, nitric, perchloric, and chloric acid. Those are the strong, the 7 strong acids, and everything after that is a weak acid. Now, there are also strong bases, and the issue with the strong bases is that there's actually not just 7 strong bases, there's kind of a lot of them, but I'm gonna give you some of them right now so that you're familiar with them a little bit. So sodium hydroxide, lithium hydroxide, potassium hydroxide, calcium hydroxide, strontium hydroxide, barium hydroxide. Basically, the strong bases are group 1 metal hydroxides, and the bottom half of group 2 metal hydroxides. Okay, so everything else would be considered a weak base. So like if your transition metals, transition metal hydroxides like iron 3 hydroxide would be a weak base, but it's still a base nonetheless. Moving forward. You learned a little bit about conjugate acid, conjugate base pairs yesterday. And conjugate acid and conjugate base pairs are really, really rooted in Bronsted-Lowry acid-base ideas. And so if a Bronsted-Lowry acid gives up a proton, what's left over can reaccept that proton and act like a base. So one of the ways that I generally sort of look at it is if I am a Bronsted-Lowry acid, and this marker is my proton, right? What ends up happening is that if I take this proton and I transfer it here, I am now proton-less, and I can now behave like a base, okay? And since you were proton-less to begin with, now that you've accepted a proton, you can now act like an acid. So when I take this back, I am now acting like an acid, and you're acting like a base. Does that make sense? Okay? So in this example here, we have hydrofluoric acid, HF, in water, and what ends up happening is that the hydrogen is transferred to the water, and the products are the fluoride ion and the H3O plus, the hydronium ion, okay? And as a result of that, what ends up happening is that the hydrofluoric acid, and in this case, the water acted as a base, okay? Now, if I take the exact same reaction and write the products as reactants, okay, I'm now going to go ahead and look at what I have and try to figure out what my acid and base are. In this case, it appears that the fluoride is proton-less, and the H3O plus happens to have an extra proton. So in this case, the H3O plus could donate a proton to the fluoride, and when it does that, it acts as an acid. And the fluoride, in this case, acts as a base. Okay? We refer to hydrogen and fluoride as conjugate acid-base pairs. And as a result of that, in this case, water and H3O plus are also conjugate, in this case, base acid pairs. For every acid, there's a conjugate base, and for every base, there's a conjugate acid in these cases. Now, so in this case, Bronsted-Lowry acid-base reactions are at equilibrium. And what that means is that the reactions are going forward and backward at the same time. So if you ever see an arrow that looks like this, it's a double arrow indicating that we are at equilibrium. In biology, when you learned about things being at equilibrium, we said that, like, well, if you took, like, I don't know, something and put it into a solution and it was dissolving and it was going to equilibrium, the substance that you added would be eventually spread out equally into the entire container. Does that make sense? Does that sound vaguely familiar? from biology, okay? So when we say that that's an equilibrium in biology, equilibrium in chemistry is not the same thing. Equilibrium in chemistry basically says that the rate that we go from left to right is equal to the rate that we go from right to left. So it's not about concentration, it's about how fast the reaction is going. But conjugate-based reactions always involve two pairs of acids and bases. So in this case, the acid is HF, and the base here is the conjugate base. And the water is the base, and the H3O plus is the conjugate acid. So they're linked together. So these two are a pair, and these two are a pair. Now, the other two statements down here are more like getting into AP chemistry style stuff, so you don't really need to understand it, but you should be aware that the stronger the acid of the two acids present controls the direction of the reaction. So in this case, hydrofluoric acid is a weak acid, but it's stronger than the weak acid H3O plus, so we go from left to right, mostly, until we get to equilibrium. You don't need to know that yet. There's math that we do to do that in AP Chem. Or there's a chart, and you don't need the chart for today, or for the scope of this class. We also learned about amphoteric substances, and those are substances that can behave either as an acid or a base, depending on the situation that they're in. So the substance is usually identified by the transferring of the hydrogen, and one of the things that you should be aware of is that the most common amphoteric substance is water. That's the thing that we usually talk about with amphoteric substances, although lots of things can be amphoteric. Now, in the first reaction, I have water reacting with hydrochloric acid. I know that I'm going to produce something that looks like this. Whoa, whoa, whoa.
What is that?
I know that I'm going to produce something that looks like this. Okay? It appears as though the hydrochloric acid transferred a hydrogen to water. So that tells me that this is my acid. And water, in this case, is behaving as a base. So in this case, water is acting like a base. Now, on the product side, though, which product most looks like the HCl? The Cl minus. And in that case, it's the Cl minus because it lost a hydrogen. So that means that this is going to be the conjugate base. So that is the conjugate base of HCl. So, as a result of that, the H3O plus most looks like water, so this is going to be the conjugate acid of water. Okay? Lastly, I have water and the NH3, which is ammonium or ammonia. But in this case, I know that what's going to happen is this water is going to transfer a hydrogen over here, and I'm going to make NH4 plus, and I'm going to be left with OH minus. So in this case, the ammonia is acting as a base, and the ammonium ion is the conjugate okay? Whereas the water is acting as an acid this time. And the OH is the conjugate base.
Wait, so then would NH4 be the conjugate acid?
So, in this case, to answer your question, if I ask you to identify the conjugate acid-base pairs, okay, you always start with the reactants. So in this case, if you identify NH3 as a base, its conjugate acid is the NH4 plus. Does that make sense? Okay? And that's all that I need you to do. But you have to understand that the reaction could be written backwards, and then in that case, it would be an acid, and NH3 would be the conjugate base. Okay? So your homework, ladies and gentlemen, is going to be in the packet that has the POGL, and I'd like you to get that out so I can show you, and you have the rest of the hour to work on it. Gets us to the end.